This lesson on transformations really is a very nice extension of everything we've been doing so far. Before we start, though, I would really like you to think about what this word transform means. When something is transformed, it's literally changed, like moths transform into butterflies, Transformers, the movie, cars turns into robots, trucks, whatever you want to call it. So keep that idea of transformation in your mind as we look at number one. The graph of the parent function f of x equals x squared is shown on the grid. Transform the parent function in order to sketch the graph of f of x equals x minus 7 squared plus 3. So here on the graph we have our original parent function, and now we're asked to transform the given graph to be what we see here. Well, we know something about this function right here. This function is in what form? Vertex form. So I know I can identify the vertex 7, 3, which means I have H and K. We can say that H equals 7 and K equals 3. From our last couple days of notes on characteristics, I know that H is a horizontal shift. This will be a shift right 7. This will be a shift up, a vertical shift. Shift up 3. So this is prior knowledge, and now we're going to see how we can take this prior knowledge and apply it to actually transforming the given graph. Our vertex starts at 0, 0. We're going to shift this point right 1, 2, 3, 4, 5, 6, 7, and up 1, 2, 3. Now, we're told that this is going to be a sketch, so it's not going to be exact. We do know, though, that we want to maintain the general width that we started with, because if I look, there's been no change on A. So when we draw our sketch, we want to try to maintain the width that we started with. And our sketch is complete. We have successfully transformed our original function by shifting it right 7 and up 3. Again, our main priority was on simply moving our vertex. The rest of these points came from a sketch, a very general sketch. Let's try number 2. And at any point, feel free to pause the video. So if you are thinking, wait, I wasn't done with number 1, go back and pause it right there, and when you're ready, press play. Number 2 says, the graph of the parent function, f of x equals x squared, is shown on the grid. Transform the parent function in order to sketch the graph of f of x equals negative 1/3, x plus 2 squared. Ask yourself, what form is this? We have vertex form again. I know that my vertex will be negative 2, 0. Remember that we have a built-in negative, so if I see a positive value, it means a negative value is plugged in. And we have a new A value to consider. Let's first look at our vertex. We know from that that H will be negative 2, K equals 0. This means a shift left 2. K equals 0, no vertical shift. No vertical shift. Let's talk about what happens with this A value being negative 1/3. The fact that it's negative, I now know that this entire parabola will now open down because I have a negative A value. And then ask yourself, will the parabola be more wide or more narrow? Well, I know 1/3 is greater than 0 and less than 1. So this will be more wide. Let's account for the shift left first. So again, we start at the vertex. I shift left 1, 2. We have no vertical shift. So I'm good to stay right here. My parabola is now going to be opening downwards, and because A is 1/3, more wide. Again, we are working on a general sketch. So let's say I have a point right here, and again, I'm choosing this to create more width. I just want to make sure I'm symmetrical to the left. So to get to this point that I arbitrarily chose to make this graph more wide, 1, 2, 3, 4, down, 1, 2, 3. So then I'll go 1, 2, 3, 4, down, 1, 2, 3. And now I can finish my sketch. So we have successfully transformed this graph. It has shifted left 2. It is now opening down, and it is more wide. Number 3 says, the graph of the parent function f of x equals x squared is shown on the grid. Transform the parent function in order to sketch the graph of f of x equals 3x squared plus 4. What are we going to say about this one? Well, we could say it's standard form, where I have a b value of 0, but we're actually going to challenge ourselves to really understand how we could actually write this in vertex form. We could write this as f of x, oh, I don't want red. F of x equals 3 times x minus 0 all squared plus 4. And the purpose for rewriting this in vertex form is to really help us to appreciate where is my new vertex going to be. Because now that I see this form, I know that my vertex is at 0, 4. And now I also know that h equals 0 and k equals 4. And I can use this information to determine my shifts. H equals 0 tells me no horizontal shift. K equals 4, on the other hand, tells me I will be shifting up 4, or shift up 4, if you just want to write shift. Make it a little shorter. Shift up 4. We also have a new a value to consider. A equals 3. It's positive, so our transformed graph will still open up. However, 3 is greater than 1. So we know that we will have a vertical stretch. Vertical stretch. The best way to describe this in words is when you stand up after you've sat for a really long time and you stretch up. Literally imagine we're going to actually stretch this graph up. So let's see what this is going to look like. First, we'll account for the vertex shift. Starting at 0, 0, no horizontal shift. So no shift left, no shift right. Straight up, 1, 2, 3, 4. And again, visualize standing up after sitting a long time, and you stretch up. Oops. So this graph has successfully been vertically shifted up 4, and this A value now being 3, we've stretched, vertical stretch of this parabola up. Notice how it's skinnier than our original parent function. Let's take a look at graph 4. Graph 4 says, graph the parent function f of x equals x squared. Then sketch the graph of d of x equals x plus 3l squared minus 1 without a calculator by shifting the parent function. So comparing graph 4 to what we've been working on, these graphs gave us a parent function graphed. Now we're going to sketch our own first. So let's first sketch our parent function. Again, we're shooting for a normal width. It's a sketch, so do your best, but something that's not too skinny, not too wide, right in the middle. So we have successfully graphed the parent function, f of x equals x squared. Now we're back to looking at what we're being given. This is in vertex form. So right away, we can identify our vertex. Keep in mind, I see a positive 3, which means a negative 3 was plugged in, which makes h negative 3. K is negative 1. And we ask ourselves, what does this mean in terms of horizontal and vertical shift? H equals negative 3 is a horizontal shift left 3. K equals negative 1 is a shift down 1. I look just to make sure there has been no change to A, so I know that there will be no change to the width. There's no stretch. There's no more wide or more narrow going on here. So we're just going to pay attention to shifting our vertex here. So I started 0, 0, shift left, 1, 2, 3, down 1. No change to the width. We just talked about that. So to the best of my ability, I will sketch this new graph to have the same width, not more skinny or more wide. And we're done. We successfully transformed the parent function by shifting the entire parabola left 3 and down 1. Question 5 says, graph the parent function f of x equals x squared, then sketch the graph of d of x equals negative, and then in parentheses I have x plus 5 all squared minus 3 without a calculator by shifting the parent function. Once again, we need to sketch our own parent function, which we can do. So we'll be sitting here at 0, 0 for the origin. To the best of our ability, we will sketch a parabola that has a normal width. If you don't like how yours comes out originally, we're working in pencil, so we should be able to erase it. And I still don't like mine. See? Even I'm erasing. That's a little better. Okay. So we have a sketch of our parent function, f of x equals x squared. Now let's see what we have happening here. I see that the function I'm given is again in vertex form, which is nice because right away, let's identify our vertex. The vertex here is negative 5, comma, negative 3, which makes h negative 5 and k negative 3. This will be a horizontal shift left 5. And this will be a vertical shift down 3. Shift left 5, down 3. Are we done? Well, we need to just double check A. Has A been changed? Yes, it has. We have a new A value. Ask yourself, what does this negative represent? Represents -1. This tells me the graph will now open down. Notice the numerical value here, if I were to ignore the sign, the absolute value of this is 1. So normal width still. Not more wide, not more narrow. The only change is that it'll be opening down. So let's account for our vertical and horizontal shifts first. So first, we start again at 0, 0, shift left. 1, 2, 3, 4, 5. Now down, 1, 2, 3. We just discussed how the width is staying normal. So to the best of our ability, we will keep it normal. And we're done. Our transformation is complete. To visualize, we took our original vertex, we shifted left 5, down 3, and now our parabola is opening down because of the negative A value. Now that we've had 5 solid practice examples on what the visual looks like with the transformations, let's switch over to a more algebraic representation and take some notes on the algebra, the language of transformations. Take a moment and look at number 6. When we see a plus C on the outside, that should jog our memories to what we saw when we're adding or subtracting a number on the outside here. So for example, this -3 on the outside meant a shift down 3. Well, here I'm adding a value. So this will be up C units. We're generalizing so that this represents any value. So for example, if this was +5, it would be a shift up 5. If this was +1, shift up 1. In contrast, if I see minus a value on the outside, that will be a shift down C units. With 8 and 9, we're going to make a connection to when I see inside parentheses x plus or minus a value on the inside. So we can visualize this one as f of x minus a -c. That's what created that plus sign. So because we're really dealing with this, that's how we know it's a shift left C units. For example, when I saw x plus 5, h was -5, it was a shift left 5. So left C units when I see plus C on the inside. In contrast, if I see x minus C, we know that that will be a shift right C units. So 6 and 7 both dealt with vertical shifts. What we're used to looking at as a K value. 8 and 9 both dealt with horizontal shifts, left or right. What we've been working with as H. H and K are now accounted for. Let's look at and contrast what we see in number 10 and number 11. Number 10 is a little more familiar to us. This is the same as saying if A is positive or negative. Positive A opens down. So here the transformation is moving from a positive A value, if I had a negative A value, Our official language for this transformation will be reflecting or reflect over the x-axis. So if my graph was originally opening up, visualize that for a moment. If I was originally opening up, here's my x-axis. A negative a would cause that graph to now reflect over the x-axis, and now it's opening down. 11 is a slightly new concept for us. This will be a reflection, reflect over the y-axis. Reflect over the y-axis. So I don't want to not put a y-axis here, but I'm just going to make it a dotted one because here, for number 10, I really wanted you to pay attention to the x-axis. When we look at this example, I'm going to make my y-axis solid because that's what I want you to pay attention to, but the x-axis is still there. So here, what will this look like? So my negative sign, notice, is not on the outside, it's on the inside, f of negative x. So if this is my starting graph, I am now reflecting over the y-axis. So my graph, my resulting graph, will be reflected over the y-axis. Negative f of x is a reflection over the x-axis. So we started here, reflected over the x-axis. In contrast, f of negative x is a reflection over the y-axis. Here is my starting function, reflected over to the other side of the y-axis. Pause here and really study these two pictures. Go ahead and grab your highlighters. Make these pictures clear in your notes, and it will help with your understanding. And we'll practice. But number 11 is definitely some new learning for us. We have not looked at this yet. We have practiced positive and negative a values with reflecting over the x-axis. This is new. So take a moment to really think about what we just talked about there. Numbers 12 and 13, we also have some familiarity with. We have C on the outside. So this is like saying we have an A value, put it in purple. We have an A value greater than 1. Well, in our graphing examples, when I had an A value greater than 1, let me go back to the front. When A was greater than 1, that was a vertical stretch in number 3. Same concept applies here. Vertical stretch when A is greater than 1. More narrow. One divided by C is generalizing when our A value is between, it's a fraction, between 0 and 1. To make a connection to one we've done, look at what happened to the graph in number 2. Here my A value was 1/3. If I just look at the absolute value, remember positive and negative just affects opening up or down. When I look just at the numerical value, the absolute value, 1/3, is between 0 and 1, and we said our graph was more wide. So to generalize here, we're going to call this a horizontal stretch. Horizontal stretch, where our resulting parabola is more wide. Checking the time on our notes. We're at 25 minutes. So I'm just going to briefly introduce this table and show you the concept for the matching activity here. And I would like you to finish trying the rest of the matching in pencil on your own for homework tonight. And we'll see what you have tomorrow. So this is a table of notes for us to reference. And really, it has a nice connection to what we just talked about. So if I see a value that's being added or subtracted inside parentheses, I know that's dealing with a horizontal shift. Shift left or shift right by that value. If I see that I have a value on the inside with X, notice C is not on the outside, it's on the inside. It's a horizontal shrinking of the graph by 1 over that value. So for example, if I had f of 5x, that would be a horizontal shrinking by 1/5. And we'll practice, but right now it matters to me that you understand the language. So f of 5x, imagine this is a 5x would be a horizontal shrinking of a factor of 1/5. In contrast, if I saw a fraction here, again on the inside, it's a coefficient of x. Let's still use 5. 1/5 x on the inside, it's a horizontal stretch by a factor of 5. Notice the effects on the x values here. You will have this as a reference or refer to it as much as you need. And we just talked about how f of negative x, notice the negative sign is on the inside, not the outside. It's a flip or a reflection over the y-axis. We just drew a picture of that. So for example, number 1, or the directions for this section says, for 1 through 10, suppose that we have this function. This is given to us. F of x equals x to the 8th. Match each of the numbered functions on the left with the lettered function on the right that it equals. So you're matching the left column with the right column. So for the moment, I know some of us are like, what? There's an exponent. It's an 8. We haven't looked at that. Don't worry about that right now. Just consider what we have written here and what we know this means. So this is my way of telling you the fact that this is to the 8th power is irrelevant. Focus on the transformation. So, for example, in number 1, I see a positive 2 on the outside. What kind of shift is that? If you want, turn back over and look what we just wrote down. When I see plus C on the outside, what does that mean? Up C units, a vertical shift up. So we will write shift up. You have options. I will accept any of these 3. Ready? Depending on what you want to write. Vertical, shift up 2. Or if you just want to write up 2, I'm cool with that as well. So you can write this full piece, vertical shift up 2 or up 2, whichever makes you happy. So now that I know what the transformation is, now I'm going to account for x to the 8th being my function. So I'm going to look for my original function, x to the 8th, with a plus 2 on the outside. Nope. Nope. No. Ah, look, choice D. X to the 8th plus 2, that's my answer for 1. 1 is D. Let's try one more. I'm going to pick number 6. F of 3x. And notice the 3 is on the inside. this is going to be a vertical stretch. So I will be looking for this same representation of 3 times x on the inside of my function, which is raised to the 8th power. No, 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 nope, no, no, yes. Notice how I have that same vertical stretch happening on the inside, raised to the 8th power. So I know that this is going to be h. Tomorrow in class, we'll make a stronger connection between what we just wrote right here with this being a vertical stretch and this concept in the table of a horizontal shrinking. We'll talk about that tomorrow. Just because I can't help it, let's do one more. Trying to read your mind and see which one do you want to do. I'm thinking number 5. Let's look at number 5. 1/3 times f of x. 1/3 times f of x. Well, if I come back over here to our notes, 1 divided by c, which represents a fraction between 0 and 1, what did that do? Horizontal stretch. So this will be a horizontal stretch by a factor of 3. So this is going to be way more wide. So now I'm visually going to ask myself, what was f of x that I was given? It was x to the 8th. So can I find 1/3 times x to the 8th? And I'm looking, starting with A, no, B, yes. 1/3 times x to the 8th. Okay, one more. So number 4 says f of x minus 2. Here I see I am subtracting a value on the inside. So you have a choice. You can look at this table. When I'm subtracting a value on the inside, I know it's going to be a shift right D. So I'm looking for that same kind of subtraction happening on the inside. So this is saying I'm taking my function and it's going to be shifted to the right by 2. Right 2. So if I look, applying this to f of x equals x minus 8, f of x equals x to the 8th power, which of these demonstrates that? Looking for a minus 2 on the inside of parentheses. Hey, check that out. G. And again, this was a horizontal shift right 2. So the general function notation represents a shift right 2, which directly matches, just for emphasis, the original x to the 8th function being shifted right 2. Right 2, right 2. So see how we do with our word descriptions, our verbal descriptions of the transformation, and how you do matching up the rest of the functions with the general transformation in function notation. So here we have our general side, and here is specific to the function x to the 8th. Give that a shot. We'll start class tomorrow comparing what you matched for 2, 3, 7, 8, 9, and 10, because I am stopping myself from doing any more. So homework tonight, finish this matching section. And then tomorrow, we will pick up with these notes on rewriting a function in terms of another function. This will be Friday's notes. Have a great night, everybody. See you tomorrow.